Good afternoon. In the last lecture, we talked about different ways of detecting Trojan using statistical testing, and what we are trying to do now is how do we extend some of those ideas to use AI algorithms. So, specifically in this one we are talking about reinforcement learning, and the key idea we are trying to extend with reinforcement learning is when you have a set of bits or a pattern and you are trying to do the bit flip, how do you do those bit flip efficiently. And in this context we introduce the idea of reinforcement learning, where an agent monitors the activity, and if the activity is towards positive direction or favorable to the objective, then you reward it. If it is not favorable, then you penalize it. In the specific example of our case, we are doing bit flipping. You either keep a bit flip or you permanently mark it as should not be flipped. And to do all of that, basically we need to use the metric somebody favorable, not favorable. Then the metric is basically scope. So, basically the values or the signals or a specific bit flip, did it make somebody more controllable or less controllable, more observable or less observable. All that metric we basically computed using one of the open source library called scope, and it has a lot of internal details, different values it gives, and you make use of that to compute whether to reward or keep the flip or whether to penalize or undo the flip. And again all these values you can compute with respect to the primary input and primary output. Some of the sample calculation for a specific gate would look like what you are computing for minimum of A and B, and for OR it would be some similar story, for AND it would be similar story. But basically you already know testability of a specific variable with respect to the testability of its input. You can compute that recursively. And once you have that, then the story exactly same as normal reinforcement learning, which is you have a design, then based on the information that you need, in our case it could have been just rare node and which would be just fine. Rare nodes as well as controllability and observability metric, then you basically you have a probability distribution of whether to flip somebody or not flip somebody, and you go back. So, I wanted to highlight two things. One is, if you recall our statistical original solution of Mero, we are essentially still trying to find a pattern, still trying to find a flip, and in that case we are saying which flip will help in the end detect. That was the criteria. Here we do not have that criteria, we are going for controllability and observability, but you can still stick with end detect criteria. It is just the flipping mechanism you reward in terms of the controllability idea. So, no matter what idea you have, if you can clearly define the objective, reward and penalty, you can use reinforcement learning. Any questions? And in this particular case we are feeding this kind of testability metrics. So, in terms of broad overview, so basically once you have the probability distribution, we are computing probability of flipping the bits, and then you basically provide it to the design, you still count the number of switches, and then essentially you continue that process, which is exactly same as the original algorithm. And in terms of number, of course, you would expect it to improve, and I am going to skip that. Similarly, for test generation time, so yes.
Compared to random test generation?
So, Mero is better than random. So, question is how better is compared to random. Mero is better than random, because random is trying to throw balls at every possible wall, and Mero is trying to throw the ball exactly to the wall where the rare nodes are. And these were supposed to be better than Mero, because Mero is flipping the bits based on a heuristic, and this is more AI enabled. More AI enabled, so it has better insights. That is why it is going to get better than Mero as well as better than Tarmac, activating all of them at the same time or activating some of them. random is always the. So, in terms of test generation time, the key idea you can look at both ways. So, typically in this community if you want to publish, you have to get to two assumptions. One is either you generate same number of tests and compare who is doing better, or you go for a specific, or you can keep running and see who is saturating at what coverage level. You can do that. You fix the time or fix the test, or you fix a coverage and say to get that coverage who is reaching faster. So, that is the test generation time, otherwise you can infinitely keep on going and generating. So, once you fix somebody, then you get the. Another aspect that is important specifically for kind of AI algorithms, any AI algorithm, is the stability. So, in terms of when you run on different benchmarks, then you want to know when you do different trial, try different times, start even if you are doing random test generation, you start with a different seed, is it stable, is the result stable or oscillating. So, then that is not a good algorithm, even if it relies on random, which is not a problem, but no matter what seed you start with, it gives you same result, could be bad, could be good, but when it oscillates or move around the trigger coverage or any metric, that is not a good idea. In this particular example, at least in this particular scenario, reinforcement learning, first it provide better coverage, that is one issue. Second is the coverage is stable across different trials. So, any AI algorithm, there are many things people look at, this is one of the thing, the robustness, how kind of stability of your algorithms with respect to different variations. Now, I am going to move to another domain, again it is ATPG, the idea I already talked about, controllability and observability, I am going to make use of it. So, ATPG stands for automatic test pattern generation, and the idea actually originated in manufacturing testing domain. And I briefly talked about manufacturing testing, but just to recap, when you do the fabrication, when the chip comes from fab, remember there are millions of them coming. So, for the processor it could be thousands to millions, for the memory it could be millions to billions of copies coming in, and there is something called automatic test equipment. You put each of the chip, remember millions of them are there, you put each of the chip on the board, run those tests, and then either it passes or it says, oh, there are few lines which are defective, right. Then at that point the company decides whether to throw in the trash bin or try to make use of it. So, for example, if few cache lines are bad, so then if it was, let us say it is a 128 megabyte cache, you have an option of selling it for 64 megabyte by disabling the remaining part. So, then there are economical choices, but no matter what it is, the key point is the amount of tests that sitting here, the tests I generated based on controllability and observability, those are the tests sitting in that tester board. You put a chip, run all these tests, and then throw the chip either left bucket, right bucket or middle bucket where you want to sell it for a lower profit margin. So, number of tests is actually important. If you can reduce it, because it is a multiplicative factor of you are going to run it for millions of chips. This is slightly orthogonal idea to functional verification, where you do once, twice, 5 times, here you are going to do millions of times. And the memory of these devices are the cost of this automatic test equipment is decided by the amount of memory you have, and without getting into the details, you have to understand you are designing a 4 gigahertz processor and the board has to run on a 4 gigahertz, although board is using a processor of the past generation which could be 2 gigahertz. So, running a 4 gigahertz processor at speed using a 2 gigahertz processor, that is a mystery, and that you can figure out offline on your own. So, where I am trying to go now, this idea we borrowed from manufacturing testing community and applied it on security validation or Trojan detection. And it is a lot of information, but it is the still same information. We need to do rareness analysis no matter what you do, whether it is a rare signal, rare branches, rare events, branch you can map to event, but whatever, then you have to do fault modeling. Remember, we are going to apply manufacturing testing technique. Manufacturing testing technique only understand faults, stuck at 0, stuck at 1 and all that stuff. So, whatever you want to solve, you have to map it to their language. You cannot speak in your mother language and expect them to understand. So, to use that tool, why we are using this tool, it will be clear in a moment. So, then you get the fault modeling, and from that fault modeling we can do different kind of stuff. So, this is click activation, this is ATPG version of tarmac click activation, this is ATPG version of Mero, and then you get the test vector and rest of the stuff is same. You do Trojan insertion and checking and testing and all that stuff. So, just to give you an idea what exactly it is trying to do. First of all, remember we had to, let me go forward the results and I will come back. So, let me go forward and then I will come back and show all of this stuff. Why are you trying to do it? So, this is actually the motivation. So, if you have in this particular example, I do not remember, about 200 signals we had, 200 175 rare signal, and our objective was to kind of do 1000 n detect 1000, that means every rare signal I want to activate 1000 times, that was objective. If you apply Mero, the statistical test pattern generation I talked about by bit flipping, as you can see some of the rare signal got activated by million times, some of the rare signal actually not visible, it may not be 0, but pretty close to 0 or 1, because those are the dark black lines. But what you really want, which is what achieved by our approach, that most of them are exactly n, nothing more, nothing less. Through manufacturing testing we can actually force it, I am going to show you that force it. I want exactly n to activate it n times each of them. But the other ones, the reason these guys are failing, you are running random test and trying to tune it in different ways through this way, that way, reinforcement learning. At the end of the day it is still random test and you are hoping and praying they will be activated n times. ATPG actually directly it creates exactly n test, give and take it did not become n, we can talk offline what are the minute details, but as you can see it is actually n. So, if you can make it n, then all the statistical guarantees hold, but in real life if some of the rare signals are very high, some of the rare signals are very low, none of them are n, then statistical guarantees will not hold, that is why you will not get 100% Trojan coverage. Any question on this particular idea? Because when you talk about rare signal, do not assume all of them has same rareness quotient, some of them would be really rare, not 1, some of them could be 0.1. So, if you keep running random tests, the one which is among the rare not so rare, they will be activated many times, while the one that are extremely rare will be activated significantly less time, and that causes this problem. And this might be a good time to talk about what happened to the diagram. So, same thing for the tarmac, because tarmac you are doing click sampling, and click sampling the basically your number of clicks and all that are supposed to go up, SAT solving time. If you do ATPG it is controlled. ATPG is kind of linear algorithm, it has its own problems because it does not talk in anybody else's language, you have to talk its own language, and few other conditions has to hold, certain paths may not be testable by ATPG. But some other point I wanted to highlight is that why is it the Mero paper got 80%, we are showing it is not even getting 10-20%. Why did it get 80%? Because it ran on synthetic benchmarks, or is I will not say synthetic, the open source ISCAS benchmarks, which are kind of toy benchmark. And if you look at their connectivity, that versus AES is also a tiny design. If you look at the connectivity, do you see a difference? What is the difference in layman terms? This is like everybody connected to everybody. Then even if you activate it somebody 10 times, your probability of activating few other people together is very high. Although n detect theoretically failed, but practically it worked. So, it took us some time to figure out why we are doing better, because when you write a paper, you not only have to explain you got result, you have to also explain the other technique did not produce the number that they reported in their paper for new designs. Because if you do not do that, then you are kind of, people may think the other people cheating, or they might think you are cheating. You are not showing their correct result which is 80-90%. You can't say, oh, they did not run those benchmarks. So, when you drastically show different number, you have to explain why those numbers are different, and this is basically the story. Now, AES is this way, other one could be even sparse, So, basically everybody, key idea is everybody is not connected to everybody. Here pretty much everybody is connected to everybody. So, that is the basically key idea for why certain benchmarks will do well even if n detect statistical guarantee did not hold. Let me now go back to where I started. So, then the problem that we had to solve, this I basically summarize. Problem we had to solve is every rare signal, let us say signal S, I have to activate it n times, and n you can choose. Typically, as I said, n equal to 1000 is good enough. If you can generate 1000 tests, that can activate it n times. So, therefore, we have to, this the way ATPG is called, you generate the first one, then you generate the n minus 1. But ATPG has a one idiosyncrasy, and that is true even for SAT solver. If you ask the same question, it will give you the same answer. If you ask give me a test, it will give you exactly same test. So, that is not n tests. So, this n time activation has to be by n independent tests. So, when you kind of follow some theory and try to run it, you say why am I not getting the results? It is because theory had that underlying assumption you had n independent tests, right. We thought we had effectively it happened to us. We generate that test, we got n of them, we did not even check they are exactly same, we got n of them, we ran and nothing happened. Not just we are not better, we are pathetically worse than state of the art. And then you say what did I do wrong, right, everything seems to be perfect, because this is not for the ATPG. If in SAT solver you ask the same condition, it gives you the same. The way you solve that problem, same thing here, same thing in SAT solver. Let us say it gave you a solution A equal to 1 in addition to other variable B equal to 0, C equal to 1, all that stuff, it gave A equal to 1. What you want to then next time you say any question you asked, in addition to that you say A not equal to 1 or A equal to 0 you provide as a constraint. You can pose the question and give a constraint by negating one of the condition in the solution. So, then ATPG would be forced to give you answer not the same one, unless there is no solution. Let us say there are 20 possible solutions, all of them are equal to 1, then of course, this will return null, then you have to try other one. So, there are little bit of that if you do not do it right, but that is the key idea. So, when you are going for n minus 1, now you see why we did not get exact n, because it does not even have an exact n solution for 1000 possible test patterns does not exist. So, every time you negate one of the assignments and you go for it and it gives you a solution. Any questions? And this idea applies everywhere. Any decent people, you ask the same question, it will give you same answer. You have to rephrase your question differently. Now, for click sampling, same idea. Only question is, instead of using a SAT solver to give the assignment, we are asking ATPG to give the assignment. ATPG has its own idiosyncrasies, but it is significantly faster, and specifically the commercial ATPG tool is significantly faster than SAT solvers in solving problem. And another thing you have to understand, the ATPG, this solution, because Synopsys adopted this solution in their this one, laser fault injection, all of them, because we were actually running on their million line designs, because they are ATPG tool that will run on million line designs. But if you convert into CNF, try to give a SAT solver, you can forget about it. As an academic exercise, as a paper is great. ATPG, as I said, it has a lot of idiosyncrasies, but it actually runs on the full design, any size design it would run.
But how do you map your this rare event thing to ATPG?
Right. So, rare event thing is basically, let us say rare event was for A equal to 1, we call it A equal to 1 is nothing but stuck at 0 for A, that is it. So, because ATPG does not understand anything other than stuck at 0, stuck at 1, anything you have, and because it is Boolean, it is much easier. If it was something else, decimal domain, then it might be little more difficult, but it is basically as trivial as this. Same thing for branch coverage, because for branch it could be very complicated. Your branch, if A and B greater than C or whatever it is, this is nothing but a condition. We create a variable x, give that condition, and create a knot of that stuck at 0 of that variable x. So, you have to instrument the design, it does not change the functionality of the design, and then we have a stuck at 0 on that element. That is what we ask the ATPG tool, do a stuck at 0 on that. So, then ATPG will give you the solution. Any questions? Now, any of you want to go home today and want to solve it, you have Synopsys, design compiler and Tetramax. This is the exact setup. This is the exact setup. You take your design and hierarchy, you write the file, you get all the different kind of library, you get still file, all that design rule check you do, and then you feed that to Tetramax and you get the test vectors. It is basically in the script we are basically putting that constraint in the basically still file. Whatever solution it gave, we parse it, put one of them as a negation, we put it back in. So, it would all work. Now, kind of to summarize what we talked about. So, on one hand, the statistical generation is basically trying to activate each node at a time and hope and pray that the trigger, which is some number of nodes, that gets activated. And on the other extreme, and this one is, or maybe the animation did not appear. So, basically when you do one at a time, this one activates, these two, maybe this, when you are activating n times, it was trying different combination. On the other extreme, you try to activate all of them or the click, and then hope, not hope, that basically the trigger would be activated, and this we talked about already. These results we talked about already, why if you do blindly statistical, why it would not work, and this scalability I talked about for click covering. Now, we are going to basically use explainable AI with Shapley ensemble boosting. We briefly talked about Shapley value analysis, and if you recall, explainable AI, there are many algorithms. Decision tree is one of the simplest one to understand, but it is not, accuracy is not great. On the other hand, Shapley and Shapley values or integrated gradients, they are, or even many of variation of large language model, they are explainable, but they could be expensive in terms of size, cost, running time, so on and so forth. So, before I begin, let me just quick recap. So, what do we do in machine learning? We have a raw data set, we kind of choose which features to use, then machine learning model, when we train, it kind of finds a boundary, cat or dog or whatever it is, and then in real. So, this is the training time. In the testing time, we are basically asking it interesting questions, showing a picture and asking, is it a cat, is it a dog, it classifies. That is the key idea, and nobody cares about training time in general, but people care about when an unknown object, not necessarily unknown, the objects that were not seen during training time, how are you doing with those objects? What is your accuracy? What is your false positive, false negative? That is all people matter. Now, normal world, there is no guideline for feature selection. Before explainable AI came in about 5-8 years ago, people were basically, it was acceptable in a paper, you just say, well, in fact, I have shown few of the features before, I will show few features. Here are the features we used, as long as that is reproducible, nobody will object. How did you come to this feature, 5, 6 of them, why does it work? Nobody will ask those questions in those days. These days people would probably ask, but there is no guideline here. Shapley value analysis helps you in that. You exactly know which feature is helpful, which feature is not, so you can rank order them. So, similarly, the training cost and model complexity is very bulky, something does not work, you keep running few more training. You do not know why you are doing, it is like your kid is not doing well in the exam, you are waking up the kid at 4 AM or making the kid study until 4 AM. So, all of them are basically without any objective functions, you are assuming making a kid work really harder and longer hours is basically a great idea. So, in ensemble boosting, I am going to talk about where basically you put less effort, you get better accuracy, and that is why the name was Trojan detection using Shapley, that is that, and ensemble boosting, this one. These two we will talk about together. And then the existing stories can provide model without any interpretability, but Shapley value analysis can provide you that. Now, here is the detailed algorithm. I am not going to bore you with the algorithm, but I want to just say you it has all the portions of a typical machine learning algorithm. You have data sampling, training, weight adjustment and feature, then ensemble prediction. Let me pictorially show you. Before I do that, I wanted to show you the features. Even for Shapley value analysis, you have to give some features initially. Even in fact, even in reinforcement learning, we did give it. You did not probably realize when we say scope and controllability, observability, those are the features. Rareness, controllability and observability, those are the features for reinforcement learning. And here, because it is a hardware design, this is number of signals or nets, number of cells or gates, fan in, how many fan in it has. So, fan in, if this is an AND gate, so fan in basically this is a 3. You might think it is a 3, but the way fan in is, it is coming from some. So, this is coming from another logic, and this was called fan out because it is going to other logic. If this is going to 2 other gate, we call it a fan out of 2. If it is coming from 3 other places, fan in on 3. So, same thing, fan in, number of flip flop and multiplexer and what not, lot of parameters. That is basically the features. And if you want to feel more comfortable with features, remember in decision tree we are trying to do, if we are trying to do Trojan detection using decision tree, I showed you other example with malware detection, it would probably something like this. So, feature 1 is more important, and then feature 2 would be number of cells, feature 3 would be number of switches, and based on certain decision you call somebody Trojan free, you call somebody Trojan infected. Can anybody tell me where did I get all the rare switches is fine, it makes sense. Where did I get this greater than 200? Why not some other number? How did I get that number?
Was it because of the entropy and Gini index?
Remember, decision tree is also a machine learning model. You need to do training, and during training I will give you all the information. I will give you benchmark, I will say it is Trojan inserted. You look at that manually or through the machine learning model, whatever it is, and you keep observe all of them where you going through, all of them rare switches is greater than number of rare switches based on some threshold greater than 200. Of course, you realize if my training set was different, there could have been one Trojan inserted where rare switching is less than 200, it is possible. Then you have to change this, and that is one of the reason this is kind of easy to understand, but not a great machine learning or explainable AI model. But all of these numbers, all of these conditions got generated after going through the training process, whether you are going through manually, you looked at all the designs, or you ran it and decision tree actually figured it out, whichever it is, that is what it is. But the good part is, if it describes somebody as Trojan inserted, you can walk back and you can explain why I took this design, called it Trojan inserted. And if it is wrong, then it is probably one of the condition was wrong that it needs to modify. Explainability gives you that insight. Instead of a black box where you just give some design and it say it is Trojan inserted, and you ask why, how did you figure that out? You have no idea. Now, how does ensemble boosting work? So, that is the explainability part. Ensemble boosting, the way it work, let us say I can't afford large language model, I do not want to use large language model, then I will use whatever model I have. In fact, decision tree will work here for ensemble boosting. In fact, this work was done using Shapley plus decision tree. So, you run the decision tree, and as we expected, result is not going to be good, it is going to make a lot of mistakes. So, then I know the mistakes, what mistakes it made. I put another decision tree whose job is to just fix those mistakes made by the first one. First one I might have trained 3 months on, I am just putting some number, let us say 300 benchmarks I ran, whether 3 months. No, but the error it made on 100 of them. This model I am going to train with 100 benchmark where it made the mistake. It does not know the other 200 or it is making correct. So, model 2 is not more powerful than model 1. I want you to understand that. Model 2 is, if you ask model 1, model 2 is good at capturing the error of model 1, that is it. And it might still make mistake, and let us say out of those 100 it probably did let us say 90 of them correctly, maybe it is still left with I do not know, just 9 of them is still left and made mistake, and it can continue until we basically have 0 left. That is the whole idea. Assumption is it would converge, otherwise Shapley. So, this is basically the idea of boosting, and then idea of ensemble, and once you have n of them, then you take the ensembled output. So, the final result is some combination of these results, because each model is not stronger than the other. This is not the final answer. Final answer is some combination of some weighted combination of this one plus this one plus this one plus this one plus this one. It is quite possible this one may have higher weight, this one may have lower weight, but it again depends on tuning and all that stuff, but each of the model is very small. Think of a decision tree, and because this is the training time, you can spend as much time as you want. During run time, all of them are running in parallel. When you give a new scenario, all of them runs in parallel, and then that parallel run basically it produces the result, and that is significantly faster. That is why it is called boosting. This is ensemble of models, and the idea of, because some simple model, lot of simple model runs in parallel, that gives you the speed up. That is why it is called ensemble boosting. Boosting is the speed, ensemble is one helping the other. Any question on this idea before I put these two ideas together to solve the Trojan detection? Okay. So, interpretation we briefly talked about earlier, that normally training when you do ML model, you have original model, and in any interpretable model creates another model. It may not be in parallel, it may be merged together, but conceptually we can view it as parallel, and it may do lot of things. For Shapley value analysis, all it tries to figure out which of the features are more powerful, can I rank the features, that is the visibility it gives. Shapley value analysis does not give the visibility like a decision tree. Decision tree gives the full visibility. Shapley value analysis only visibility you get, ranking of features, that is all you get. So, with that, and just to recap, how did Shapley value analysis work? Basically it creates a competition of so it computes the contribution of different feature through a competition. If there are 3 features, to find out how much one is contributing, it is doing 1, 2, 3 working together versus only 2, 3 working together, and subtracting that result or gain in a competition, and they do average of all these scenarios. That is basically contribution of 1. They have to do same thing for 2, same thing for 3, and when you have a lot of features, it is going to take a lot of time, but this is actually in the still training time. And if you want to see pictorially, you have a lot of data. In this particular case, these were all of the benchmarks, think of Verilog benchmarks, and you are trying to figure out do they have Trojan or they do not have Trojan, and these are the initial some features, name is not important, and then you run that decision tree. Remember, you are trying to do ensemble, you run that decision tree. Now, it might be a confusion, wait a minute, decision tree and explainable AI model, Shapley value analysis and explainable AI model. In this work we combine both. Shapley analysis is only Shapley, decision tree is giving ensemble. We wanted to do this Shapley ensemble boosting, we came up with this term, no term existed. So, then we do Shapley analysis when this decision is happening, Shapley analysis, and we are doing weight adjustment, because in this example what we are seeing is, so black dots are unseen sample, they have not been analyzed yet. The green dots are correct prediction it made, whether it is Trojan or not Trojan does not matter, it made correct prediction. Red ones are the mistake it made. So, then when I, and then Shapley analysis is doing the which of the feature are top, which of the feature are bottom, it ranked them, top ones are higher ranked, bottom ones are lower ranked. So, for example, whatever the name is, this is higher ranked, this is lower than that. And then we run another decision tree and continues, and the assumption is now it made 2 error, this would have 1 error, this will have no error, right, and it kind of different features, different type of features. So, red one is high impact feature, blue one is low impact feature. So, that thing kept changing, this different one became high and low impact. So, that is basically the whole story, and that will give you the final ensemble prediction whether you have a Trojan or you do not have a Trojan. Any question on this idea of Shapley ensemble boosting? You start with a set of benchmarks, you run, you make some mistake, put somebody just to fix those mistakes, and this is during the training time, all of it during training time. It may take a long time, but once this is done, then basically you simply run, you give a design and all of the model runs in parallel on that design to produce a result. Same, produce a Boolean output. This is a classification example I talked about. You could do similar stuff with regression also.
Sir, this is same like random forest or like it is different?
No, this is not a random forest, because each stage we are using only one tree. We could solve that problem using random forest. Instead of one decision tree, we could use a random forest right here.
So like in random forest we take lots of tree and then use, and the output of each all the tree we combine.
Right,
So
absolutely. But all I am saying is, if you want to do random forest, visualize this single tree as the random forest in itself. Each stage a set of random forest, and then eventually we are going to decide something. If you want to use this Shapley ensemble boosting idea,
Okay.
we could have done that. And your idea is well taken, that why are we doing all this stuff instead of Shapley? We could have done random forest. Absolutely, you can try that and try to beat this result, then that is going to be a paper. Any other questions or comments? So, now anytime you do any work, you have to show lot of results, and now that we are diving into deep into AI, most reviewers want to see all of these. Accuracy, of course, everybody want to see, but they want to see precision, all these names. Let me spell it out. So, true positive, true negative, false positive, false negative. True positive is that when it says it is Trojan free, that is indeed Trojan free. When it says Trojan inserted, it is indeed Trojan inserted, and false positive, false negative is inverse. You want the accuracy is all of the decision, and on top is true positive and true negative, correct decision by all decision, that is your accuracy. And similarly, there are recall, F1 score, and many such numbers, and each has its own interpretation, people are interested. And when you kind of compare, so this one is random forest, then CNN, this is reinforcement learning we talked about earlier, the reinforcement learn test generation using reinforcement learning, which is flipping the bits using reinforcement learning, and this one is Shapley ensemble boosting. And basically you want to show accuracy is high, and you also want to show, there is a lot of numbers I am going to skip, but basically you want to show that accuracy is high, and your time taken to do whether training, whether to testing, all of them are low. That is what you want to show. But what is the important part, the explainability part, I want to just zoom in little bit. So, for each design based on certain number, every design has a kind of a interesting number. For this particular benchmark, EFX is 2.192. So, if your final feature value, think of for AI model, this is the line. Remember, when any AI model we give, what does it do? All these points they learn, they kind of create a line. Let us say it is a vertical line 2.192. If final story is on the left of something, then it is basically Trojan free. If it is on the right of something, so this is Trojan free, and this is basically Trojan inserted. So, this is basically Trojan. So, that is the 2.192 line. Now, how ML model gets that line, we can talk offline, but basically now that we have that line, what are these features doing? Every feature is like doing a tug of war, it is pulling in a direction. So, for example, I am going in reverse direction, out of these 3, 4, 5, 6, 7, out of these 8 features. So, the bottom one output flip flop, that is pulling to the left by very tiny margin, saying I believe it is Trojan free, and wherever it stops, that is where the next one starts, not on that line, and it say no, I do not agree with you, I think it is a Trojan insert, and then it try to pull that direction. wherever this stop, that is where this one starts and say I do not agree with you, and this one says I do agree with you. So, this forward backward later, when all the features are done, question is where is the final line, and is that on the left of 2.192 or right of it. If it is to the left, now how is it, how this Shapley analysis different from normal machine learning? Normal machine learning, knowingly unknowingly they are doing similar stuff, some stuff, eventually they are coming at one point. They are also use a notion of marker, either you are on this side of the marker or that side of the marker, this side of the plane or that side of the plane, right. So, this particular, and same thing if you see another design. So, or another same design with Trojan inserted, it started with here everybody pulling pushing later, final result is on the right of that line. So, this is basically then this is Trojan free, that one is Trojan implanted. Any question how explainability? Now, how is, so this is basic, this information Shapley analysis will give you. What you want to do with it? Let us say you gave a new design and it made a wrong prediction, then you know whoever you made highest priority, who pulled the maximum, because two people pulled the maximum on the this direction. If this design happened to be Trojan inserted, you want to reward the people who tried to pull on the right direction. Specifically this dude, it tried so hard, Nets tried so hard to convince everybody it is Trojan inserted, but these two people tried so hard to pull it back. So, you want to penalize these two people and push it down in the priority, in the ranking. You want to promote this particular one up. Now, it should not be a brainer that the two people who are doing on the top in the story is rare switches and dynamic power, because rareness is the bread and butter of Trojans. So, even before AI explainability you could have predicted it, but when you are trying to apply explainability on new domains where you do not have enough insight, it will tell you that, and then you can say, oh, that makes sense, that makes sense. Same thing for dynamic power, because it involves switching, which I will come in a moment. Any question? Now, when you do multiple benchmarks, story would be different, but nonetheless they will collectively, all these things will pull you. There I zoomed into one circuit, here 10 circuits, some circuits are pulling towards left, some are pulling towards right. The one going towards left are Trojan free, the one going towards right are Trojan inserted. So, one thing I wanted to show you, robustness, and this is another aspect any reviewer would want to see. What is the robustness in this context? Robustness in that context is if you go for different trial, how stable your solution is. Here robustness means something else, and which is if you are saying something is Trojan free based on certain feature, attacker knows that, attackers try to play with it. They want to bypass that, that is known as adversarial. We remember adversarial machine learning, where a stop sign would look like a yield sign, all that we talked about. If somebody do that, you see random forest from 75% accuracy, it went down to 44%. 44% is like random guess, as bad as random guess. 88% it went to 33, very bad. So, TGRL also went very bad, even Shapley ensemble boosting went very bad, but the important part now to observe, it is all became bad as a random guess. What is important when you retrain it? Anybody knows how to do retraining? For a kid example, retraining is make the kid study even harder. That might be the reason kid is doing bad, put more pressure on it. That is the retraining happened in situation like this, where you do not have explainability, although that is technically not correct, it improved, it went very close to original result. When you do retraining, even this one also went very close to this one. So, TGR, the reinforcement learning one went up, the Shapley ensemble went really up. So, the retraining time explainability gives you an advantage, which is you exactly know why things went wrong. So, when you retrain with a data set, images, whatever made a mistake. If there is a cat which has a ear like a dog, you want to just put few more training samples where the cat you label that example that looks like a dog as a cat and train it. So, retraining is a great idea, but during retraining time you have to give guiding examples, right examples. If you give too many examples, that overfitting problem. If you give wrong example, you are going to do even worse, but none of them actually become worse. But the key idea people want to see, adversarial story will happen, how quickly you can recover and give good results. That one aspect people look at. Second aspect people look at, how much time do you need for retraining. I believe this is in seconds or minutes, I did not remember, but the thing is how much time do you need. So, the reinforcement learning took most of the time, a lot of time, because of the learning agent and all that stuff, and Shapley took very little time. So, now I am going to start talking about Trojan detection using something orthogonal approach. This may be a logical time to take a break. Do you think we should do? Let us take a break. After the break, we will talk about Trojan detection using side chain analysis.